Hello and welcome back to Precalculus. Today we are talking about the zeros of polynomial functions. Eventually, when you learn enough of other functions, you will realize that polynomials are the evil ones, right? Because it's really nasty to find zeros, and today's lecture is just, one attempt to find zeros, because as you are going to see, there is no other way unless you are using technology, which we have opportunity for today. But just thinking 50 years ago, right, where even the calculators were not the thing, trying to solve a polynomial of some kind was insanely difficult. You will find that finding zeros of trigonometric functions, exponential, logarithmic functions were all going to be a joke, because you learn like 3 or 4 rules and you just go and figure it out. These guys, not so friendly. Now, why? Why is it so? Well, without going into mathematical theory and all of that kind of stuff, I'm just going to point out few examples that you guys know, and then point you to reference for others, and then give you a statement, and then we move on. So, if I have a polynomial function 3x plus 6, and I want to find the root or x-intercept or a zero, those are all the same names for the concept. I mean, different names for the same concept, that's what I meant. You know that you are supposed to set y equal to 0. That's why it's called a 0, right? You're looking for the x value where y has the value of 0. Also, why is it called a root? Well, should be clear. Root.
Is that actually why it's called a root?
Yeah, exactly. Because if this is your x-axis is the ground, this is exactly where the root starts. Yeah, there you go. It's so simple, right? So x-axis, x-intercept, root 0, that's it. It's all the same. It just means this thing that the function goes through, that x-intercept value that the function. What is that x equal what? Right, that's your root. All right. So now we clear that up. I say set y equal to 0. Well, that is a joke, right? So x equals -2. Right? You move 6 to the other side, you get -6, you divide by 3, you get -2, and that's your root. We're done. Woohoo. Then we move to the spicier case, right? X squared plus 3x minus 9, right? You go, oh, I can't factor this one. The middle term doesn't really go. Oh, that's okay. I know I have a formula to figure out roots of quadratic, right? There it is. And then you stuff these values in and massage it with PEMDAS, and out comes the value, right, the roots. And you got 2 roots over here, because you have this plus minus situation. So you have to separate the calculation at that point and then compute 2 different values. And sometimes it can spit out complex numbers. We might run into, I just wrote anything over here, so we might run even into complex numbers. Let's see what we get. No, we're not going to get complex. So -b, that's -3, plus minus square root of 3 squared minus 4 times 1 times -9, divided by 2 times 1. Right, your a is 1, your b is 3, your c is -9. So, -3 plus minus square root of 9 plus, is that 36, divided by 2. So, -3 plus minus square root of 45 divided by 2. And we can just make it a little bit nicer here, because I can write square root of 45 as square root of 5 times 9, so 3 root 5. That's the best we can do if we want to have the exact answers. So you have two roots. X1 is negative 3 plus 3 root 5 over 2. And the x2, the second root, is negative 3 minus 3 root 5 over 2. So two roots. Well, of course you're going to expect two roots because it was a squared problem. Now, the next one, right, would be, the next polynomial with the order up would be the x cubed problem. And the simplest problem in that category would be y equals, well, not the simplest, but one of the standard problems would be x cubed minus 1. Okay, the formulas for this are horrendous. Look it up online, right? Look up the formulas for cubics, and you will see that they take, a page of calculation and 20 minutes of your life to get to the first root if you want to use the formula. So we went from a single simple calculation into, let's review every single operation we ever learned, into the formulas that, just to write the formula, it takes 2 lines, just to write it. And then it's going to take you like 20 minutes to compute through that. Now, when they're nice, something like this, right, maybe we can say, oh, okay, x cubed equals to 1, because you start by equaling it to 0, right? To find the root, you set equal to 0. And then because this one is nice, you can do this. Then you have your cube root of x cubed equals to cube root of 1. And then you get your x equals 1. And then you say, wait, didn't you say that we should have 3 roots for a cubic and 4 roots for the 4th degree and 10 roots for 10th degree? Yes, I did. Right? So what are my other 2 roots? Uh-huh. Okay.
Wait, shouldn't that be x equals cube root of 1?
It is cube root of 1. And then cube root of 1 is 1.
Oh, yeah.
So now we get to play with the factor theorem and all of that stuff. Aha. So if this puppy is a root, that means that x minus 1 is a factor. Which means that I can divide x minus 1 into x cubed minus 1, and I will get some kind of x squared polynomial, which I can crank using the quadratic formula and find the other 2 roots. Let me repeat this just in case that for a moment you didn't pay attention, because this procedure that I'm going to talk about again now is the procedure that is like the thinking behind every problem we are going to see in 2.5. So you were able to obtain one of the roots somehow. It was given to you in a problem. You were able to do some of these cute calculations through factoring or whatever other witchcraft to come up with a root. It was communicated to you in a dream. I don't care how, but you got one. You have one root. And you know that number of roots corresponds to the order of the polynomial. So, I have one root. I know I have to have 3 roots. That means that I can use this one root to reduce my cubic into quadratic, and then when I use quadratic formula, it's going to spit out the other 2 roots. So, when I did this and I came up with x equals 1, I know that's a root. And by the remainder theorem, sorry, the factor theorem, I know that because x equals 1 is a root, I know that x minus 1 is a factor. which will divide evenly. Okay, that's good. So now I know that if I divide x minus 1 into x cubed minus 1, I'm going to get some kind of x squared here, polynomial, which I can hit with the quadratic equation. Now, we are not going to do this long division. We're going to do our synthetic division, right? Because we are bosses over here. So, drop the 1 down. 1 times 1 is 1. Add down. 1 times 1 is 1. Add down. 1 times 1 is 1. Boom. This is your first checkpoint. If you get a remainder, that means that either this is wrong or your calculation is wrong, something is wrong. Because that has to be 0. By the theorem, if something is a factor, remainder is 0. So you can use it as a checkpoint. Cool. What is my quadratic? It is x squared plus x plus 1. Aha! So that one, that polynomial right there, is hiding the other two roots of the problem above. Let's go find them. A is 1, B is 1, C is 1. Negative b plus minus b squared minus 4ac divided by 2a. Oh, great, they're complex, right? Well, of course they're complex, because a lot of people don't know they even exist. They just say, oh, cube root of 1 is 1. Yes, and what else? So we're going to see what else. This is negative 3 now under the cube root. And then we have a 2 over here. So now, a little bit of our complex numbers. Negative 1 plus minus a root 3i over 2. There they are. They're complex, but that's okay. We should not discriminate, right? Be decent people like once in your life. So these are my x1 and 2. So what do I have? I have a root, or x2 and 3 actually, because x1 is... So x1 was 1. Second root is negative 1/2 plus root 3 over 2i, and x3, third root, negative 1/2 minus root 3 over 2i. There we go. 3 roots. Now you will say, well, these are complex. Yes, they are complex. And they bounce off. No, they don't bounce off of the x-axis. They bounce off in space somewhere, right? Because they have imaginary I in it, right? So we said that they don't go on axis. They don't go on x-axis like the other roots. So now we understand that when we have a polynomial, we need to reduce that polynomial with the roots we know. We need to reduce that polynomial with the roots we know. And then the remainder, hopefully, is going to be, right, the remaining polynomial is hopefully quadratic, which we should be able to do through quadratic function. So let me now make up a problem, another problem that's going to be simple, right? And then work. So let's say that we want all the roots to be integer numbers, like -2 and let's say 3, and then whatever else. It doesn't really matter what I pick. I don't know why I have difficulty to pick random numbers like this. Like literally anything that I put will be fine. 1, I don't care. So if these are roots, I can make x plus 2, x minus 3, and x minus 1 factors, right? So they always have opposite signs because of that x minus c business, right? So now, if I FOIL all this mess, I will get a cubic polynomial. Okay, let's FOIL the first two. That's going to be x squared minus x minus 6. And then we now need to multiply that by x minus 1. Okay, so that will be x cubed minus x squared minus 6x minus x squared plus x plus 6. Awesome. And for the final polynomial, x cubed minus 2x squared minus 5x plus 6. That's what we have. I hope it's correct. All right, cool. So this is our situation. This is what we have. So now what? Well, we have our terms and everything. We want to find a way to bring these guys back, right, into the factors. Because you will see later on in mathematics, you always want to have factors. Like having a polynomial is great, but having factors is way better. And the goal of this section, lecture, whatever, is to learn a method that sometimes works, to learn the method to deal with this. Now, what we have done so far? We have done the linear, we have done the quadratic, we talked about the cubic and said good luck. The quadric, the one with the 4th degree, is absolute insanity to do. I remember trying one once. It took me an hour to grind through calculations to get the first root out of the procedures and formulas. I got that wrong and I gave up because I said I want to play video games. I did not want to invest another hour, right, into redoing the problem and then still probably making a mistake because calculations there were insane. Now I was a student at that time and I was interested. I just wanted to see what kind of horror, right, we can expect from these calculations when, anytime you see huge procedures and formulas and stuff like that and it can be simplified, you're dealing with something evil, right? Now, there is also mathematical proof which says that mathematical formulas for factoring degree of 5 and more cannot exist. So it's not no one figured them out because all of these other formulas, right, someone had to figure them out first, right? So we have them today and we know them today. But there is a mathematical proof that says that x to the 5 and above cannot have a formula or a procedure associated with to find roots. So if you can't factor or if you can't do what we are going to learn now, you have to use computer or intermediate value theorem or something like that to grind and figure those roots out. So yeah, polynomials are very nasty for that. So the easy ones, right, the linear, quadratic, right, those are the ones you deal in algebra. And yeah, sure, it looks like that. But as soon as you get x to the 7, that's it, game over. You either are lucky to see that factoring by grouping can help and here and there maybe something can do something, but for vast majority of them, the only thing you can do is cry. Or use numerical methods, as I mentioned, or something of that sort. Okay, so now let's learn this new method, staring at this polynomial, of what is called possible rational zeros. I abbreviate that as PRZ, because PRZ, right? So I say PRZ because I can roll my R's. I don't know if you can roll your R's, but I can. So I call it PRZ. So possible rational, oops, I forgot the A, zeros. PRZ. All right, so what is the possible rational zero? I should have done this in red because this is the This is the thing you need to know. So you are going to take factors, and I'm just going to put all over here and put 7 exclamation points. 7, I said. There we go. All factors of constant term divided by factors of the leading coefficient. Coefficient. Okay. So, applying that on the black equation you see on top of the screen, PRS is equal to what? Okay, what are all of the factors of the constant term? Constant term is 6. Factors of 6 divided by factors of 1. Your leading coefficient is the highest exponent, which is x cubed in this case, and the coefficient in front is 1. We don't write 1, but we know it's there. 1 times, right? So what are the factors? What are all factors of 6? Well, all factors of 6 are plus minus 1, plus minus 2, plus minus 3, and plus minus 6. Factors of 1 are just plus minus 1. So what is your PRS now? It's the list of possible rational zeros for the polynomial up there. And that is 1 divided by 1 is plus minus 1. 2 divided by 1 is plus minus 2. Plus minus 3. Plus minus 6. Now, obviously, sometimes this is going to have more, so you will have more divisions and all of that kind of stuff. All right, what you got here is the list of 8 numbers, and some of those numbers could be your roots. I know you know all of the roots because we use them to construct a polynomial, but the problem that you are looking at is find the roots of BAM. You have no clue where this came from. So you're looking at this problem and you say, okay, we do the PRS, possible rational zeros. So you get the list of possible rational zeros. In this case, you have 8 numbers. Sometimes you're going to have 12, 24, whatever, right? There could be fractions in there. So now, your job is to figure out which of these are your roots. And then you're done, right? Because when you have roots, you have factors immediately. Okay, so how do I figure that out? The synthetic division, right? See, you're assuming that x equals plus 1 is a root. And now you have to check. And you know how to check. You stick that in the synthetic division. What is the problem? 1, negative 2, negative 5, and positive 6. And you are hunting for that 0, right? That's what you're hunting for. Let's check 1. Drop 1 down. 1 times 1 is 1. That's negative 1. Times, that gets you negative 1. Gives you negative 6. Ooh, we got it. So, because remainder equals 0, x equals 1 is a root, and x minus 1 is a factor. Awesome. Now, even better, what it left behind over here is the x squared minus x minus 6 polynomial, which you can continue this guessing, or you can just hit with the quadratic equation, or if you can factor, right, by looking at it, and then you're done. So let's say you don't know that the factors over here are negative 3 and 2. So you just say, okay, let me use quadratic equation, right, to be safe. So that's negative b, which is negative, and negative is positive. Negative 1 squared is 1, minus 4ac, so that's a negative 6 there, over 2. And 1 plus minus, that's a negative 24, positive 24, positive 25 over 2. So you are getting over here 1 plus minus 5 over 2. Boom, boom. 6 over 2 is 3, and negative 4 over 2 is negative 2. So I have x equals 1. That gives me the factor x minus 1. X equals 3 gives me the factor of x minus 3. And x equals negative 2 gives me the factor of x plus 2. Is that what we have? Oh yeah, right? Those are the ones we started from. Again, you are not given this. I use this to make your problem. I know what the answers are because I use that to make the problem. You are picking up the problem here. You have no clue of anything up there, but you can find it by using the possible rational zeros and then testing the numbers until you hit the jackpot, which is a root. Once you hit that jackpot, you use that root to reduce your polynomial, and if you are at the quadratic level, you can just hit it with the quadratic equation. Let's see another example from the book. Using PRS, possible rational zeros. I'm just going to jump in a homework section and pick something up from here. I'm trying to see something that it's not going to be the same as this one. They're all cubed actually in this section. So whatever. We'll do more examples, not just one. So I don't want to waste time here looking at this for 20 minutes, right, and not doing the work. So let's start with number 12 because we can, and then we'll do something else. So f of x equals 2x cubed. We'll do higher exponents later. 5x squared plus x plus 2. Good. Roots, factors. Sometimes you just say factor, right? Factor this, right? And good luck, technically, right? That's what it says. All right. So how do we do this stuff? Well, first, factors of the constant plus minus 1 and plus minus 2 divided by the factors of the leading coefficient. Okay, that's great. And now 1 divided by 1, and then 2 divided by 1, and then 1 divided by 2, and then 2 divided by 2, which is what we already have. That's this. So we don't have to list the repeats. So these are all the combinations of dividing these guys. And you see you have 6 numbers. So I divided 1 by 1, I divided 2 by 1, and then I'm done with divisions by 1. I divide everyone on top by the first one, and then I divide everyone on top by the second one, or how many I have on the bottom, right? So I only have 2 now. So I divided 1 by 1, that's this. I divided 2 by 1, that's this, and then I'm done with 1s. Then I move and divide by 2s. 1 divided by 2 is a half. And then 2 divided by 2 is 1 again, so I don't have to write it. So once you exhaust all of these combinations here, you have your possible rational zeros, and it's time to start guessing, right? You can either go in order, or maybe you can pick and get lucky. Maybe. So let's start with x equals 1. Boom, 1. Problem is 2, -5, 1, and 2. Drop down 2, 1 times 2 is 2, add down, that's -3, add down, right on the money. Really? Wow. Should have bought a ticket today. Because look at this. Sometimes you have to do like 5 of these before you hit 0. Like I got 2 in a row. Well, kind of cheated on the first one. I knew what was going to happen. But on this one, I had no clue. So, x equals 1 is a root. X minus 1 is a factor. Haha. Awesome. And I got 2x squared minus 3x minus 2 to continue working on it. Well, I'm just going to stick all of that in a quadratic formula real quick and be done. So that's a 9 minus plus 16. Ooh, that's going to be shiny. And then I have 2a, that's a 4. Great. So that's 3 plus minus square root of 25 over 4. And I have my other x equals 3 plus 5 is 8 divided by 4. 3 plus 5 over 4 is 8 divided by 4 is 2. And 3 minus 5 over 4 equals -2 over 4, which is -1/2. So now I just get to do this. And, right? They were on the list too. Like if I continued guessing, I'll get them as well to give me 0 and a remainder, telling me that they are roots as well, if I continued guessing. But since I reduced it down to a quadratic, I can get faster through quadratic equation and get the 2 roots at once rather than guessing. Because guys, those 2 last roots, they don't have to be real numbers. This is not going to detect complex, where the quadratic will, right? So right now we're just lucky that we had all 3 positive answers, real answers. But you could have had, 1 real and 2 imaginary answers, complex answers, right? And at that point, good luck, right? Because your other method is not going to work with guessing because they are not on the list. You don't have any complex numbers on that list up there. So it's very useful to know what values you're going to use.
Can I
Go ahead.
ask, how do you know, like for x cubed minus 1, how did you know that there's 3 roots? Is it just because it's the exponent or something?
Yes, very good. Every time. The exponent tells you exactly how many roots you have. That's a mathematical rule.
So if you go like to x to the 4th or x to the 5th, it would be 4 roots or 5 roots?
Yes. 4 roots for x to the 4th, 5 roots for x to the 5, and so on. There are never exception to the rule. Mathematics is very, very particular. There are no exceptions to the rule, ever.
All right, thank you.
All right, cool.
Can I just make sure I'm understanding this right real quick? So the 3 roots of the 12, the one we just did, are 1, 2, and -1/2.
Yes. Well, I didn't finish that. Now I need to write this. So I have a root. I have a root of x equals 1, which gives me the factor of x minus 1. I have a root of x equals 2, which gives me the factor of x minus 2. And I have a root of x equals -1/2, which gives me the factor of x plus 1/2. If you want to check your work, the only thing you need to do is to multiply these, and it will come up as that. Now, it could be off by a constant, but we need to discuss those types of problems when we are done with the pers over here.
What if the finding the x1 root through synthetic division doesn't work? Like it doesn't come out to 0.
Then you move
The
to the
remaining.
next number in your list until it works, which is why I said I should have bought a lottery ticket today rather than teaching a class, right?
Oh, so
Because
we try the next factor, like
exactly,
2,
this is
3.
why I wasn't too happy that I got I mean, it sounded like I was, and then it wasn't, and it was all confusing with emotions there. Because I need to show you, right, you as a student, I need to
Oh,
show you that this is, not something that will always be, oh, I just do the synthetic division and boom, out comes the root. That's like very rare, right? You have to go
synthetic division.
to, yeah, you have to
So for
go
the
to
one
a
we just
couple of them.
used,
Go ahead.
gotcha. So for the one we just used, if 1 didn't work, we would have used 2, and if 2 didn't work, we would have used 1/2.
If 1 didn't work, then the next number in line could be 2 or could be -1. Some students like to do +1, then -1, and then take that out. Then you use +2, then a -2, then you took that out. Then you have a +1/2 and a -1/2. There are 6 numbers here, right? And you can do that in any order you want. Now, in general, people do 1 and then -1, so they can just take that off the list. They cross it out. And then let me try these two guys, cross it out when you're done with both of them, right? So we'll see. I mean, it's just so it happened that I ran into a problem that worked on the first shot again.
So you could have like 10 different factors and you'd have to test pretty much all of them before you reach 0.
Depends on your luck.
Yeah.
Okay. That's the best answer I can give you. Depends on your luck, because literally, right, you don't know which one it is. I don't know which one it is. We just go plow through all of them, and eventually one works. That reduces your problem. I just want to try one of these higher exponents. Let's do something with x to the 4th. Here, number 3 has a couple of them. So your f of x is equal to 3x to the 4th minus 11x cubed, lock the doors, right? Minus x squared plus 19x, holy nightmare, plus 6. All right. Always the same factor, right? Which means you will find factors, you will also have roots, right? So all of that stuff is going to click in one spot. Okay. Pers, possible rational zeros. Constant, plus minus 1, right? Constant term is 6. Factors are plus minus 1. Factors, all of the numbers that 6 can be divided by evenly. So I can divide 6 by 1, I can divide 6 by 2, I can divide 6 by 3, and I can divide 6 by 6. On the bottom, leading coefficient can be divided evenly by 1 and by 3. The numbers you don't want to have here are 12, 24. Like, these numbers have insane amount of factors. It makes your list like ridiculously long. But obviously there are problems with 12 and 24. Just wait for your MyMathLab homework. You're gonna enjoy it. All right, so now I'm dividing by 1, which means I just get to copy the list as is. Right, I'm dividing by 1, so these numbers do not change. And then I am dividing by 3. That introduces 1/3 to the list. It introduces 2/3 to the list. Now 3 divided by 3 is 1, I have it. And 6 divided by 3 is 2, I have that as well. So we just had, is there a way that I can squeeze this in? Plus minus 2/3, terrible, but it's there. All right. How many numbers? 1, 2, 3, 4, 5, 6. I have 12 possible roots here on a pile. And I don't know if 1 is going to work. Maybe it is. Maybe if it is. Maybe if this works, I should just end the class and go buy a ticket right away. So 3, negative 11, negative 1, 19, and 6, right? Let's go. Drop 3. 3 times 1 is 3. You get negative 8 when you add down. Negative 8 times, add down, you get negative 9. 1 times, you get negative 9. Put it down to 10. Finally, we got the one that has 16 on a remainder. So, bad. So here it is, finally failed. We did not get 0, which means we have a remainder. If we have a remainder, it did not divide evenly, therefore 1 is not a factor. We send 1 home, and we go and try negative 1. Like that. That could be our next stop in life. So let's go. We are testing negative 1. 3, negative 11, negative 1, 19, and then 6. Boom. Drop down 3, negative 3, because 3 times negative 1 is negative 3. That gives me negative 14. When I multiply them, I get positive 14. When I add, I get positive 13. When I multiply negative 1 times 13, I get negative 13. When I subtract them, I get positive 6. Ooh, there it is. I get negative 6, and there is the 0. So, x equals negative 1 is a factor. Oh, sorry, root. X plus 1 factor, right? The opposite sign. Okay, now, the problem that I have on the bottom is x to the 3, right? This would be 3x cubed minus 14x squared, blah, blah, blah. So I can't put this in a quadratic equation. So I am going to start with that one.
Oh, so you're just doing like the same thing again.
Yes, very good. But the next time I hit the root, the leftover will be quadratic, and I can hit that with the quadratic equation. So
Are you
now,
using the same list of pers?
yes, but I'm just going to continue down the line. 2. There could be another root of minus 1, because there is no problem to have, x plus 1 squared and then x minus 3 and x minus 2/3, right? You can have this, like 2 roots, right? We know multiplicity last time. But you know what? Chances are you might not. So continue with 2. Drop down. 2 times 3 is 6. That gives me negative 8. Gives me negative 16. Then that's negative 3. That's negative 6. Oh. X equals 2 is the root, and x minus 2 is the factor. Now, do you want to risk and go again with numbers from the list? You can. You might feel adventurous, right? So you just go and do it. Or you can just say, oh, this is 3x squared minus 8x minus 3. And then let's go. Negative and negative, so that's negative b, that's 8. Plus minus square root of 64 minus 4ac, that's going to be a 9 there, right? 3 times 3, yeah. It's a negative 3, so that's a plus there even. Over 6, right? Just plug all of that stuff in. It's going to be 36. Ooh, 100. Square root of 100. That's a 10. That's nice. So we have another root, which is 8 plus 10 over 6. And we have another root, which is 8 minus 10 over 6. 18 over 6 is 3. Negative 2 over 6 is negative 1/3. Yep, 3 and negative 1/3 were both on the list. So I have a factor x plus 1. I have a factor x minus 2. I have a factor x minus 3. And I have a factor x plus 1/3. There you go.
When you were doing the second set of synthetic division, after you already got rid of the first root, or I guess, yeah, the first one, why are you still using the 3 that came from the x to the 4th? Wouldn't you have to bump that one off and use negative 11x to the 3rd to start it off?
I am not. Why am I using? Can you repeat that? Because I didn't really understand the question.
Yeah, sure. So to find the root 2, or no, the root negative 1, we did 1.
Yes,
and
we did that here.
Yeah, 3, negative 11, all that.
And then I carried that there.
Yeah. So then, but now we already found one of the roots.
Yes.
So now we're treating it like it's like
a new problem.
Cube root.
Yes. Because this is 3x cubed. Yes. Go.
That's 3x cubed. But wasn't that 3x? Wasn't that 3x to the 4th a second ago? Oh, we're just bumping everything up one?
Down one.
Oh,
because,
yeah.
Because technically you divided by x plus 1, which is why it went from x to the 4th now to x to the 3.
Okay. Where did the negative 14 come from? Because before that, we were using negative 11.
Right? Through the synthetic division, the polynomial that you get as the answer is the new polynomial.
Okay. I didn't realize we were plugging in the answer from the synthetic division into the new problem. Oh, I thought we were using just the original equation.
No,
okay.
Because you reduced it down to the next polynomial down. Now, yeah, it happened to have the same number on front and the back, and yeah, sure.
Yeah, that's what confused me. Yeah,
but yeah, this is like a new problem, but because it comes from the same set of answers, we still can use the same list of roots.
All right, I get it now. Thank you.
You're cool. All right. Now, one more concept here, and we are done for the night. We'll pick up next week.
Oh wait, Professor.
Yes.
Sorry if you like answered this or if it's a dumb question, but does the leading coefficient, does that tell you how many roots there are? Like this past problem, it was 3x to the 4th, and we had 4 roots, I think.
Yes, it's not leading coefficient; it's a leading term, the power. The power, not the right. The power of the root. So our power here was 4, and that's why we had 4 roots.
Okay.
Exponent.
That helps. Okay.
Awesome. All right, so now let's go and see what we have for the this last. I hate calling these type of problems, but it is actually the way we come up with problems and examples for all of this. So what I'm going to have here is the now I'm going to give you. Technically, we're making a polynomial, so I'm going to give you roots, right? And you're going to look at those roots, and you're going to create a polynomial. Now, how's that done? Well, simply through just multiplication, right? That's all it takes. You have a couple of these roots. You create factors, and when you create factors, then you have everything you need to do the rest. So let's go and see. The problem says find the polynomial given roots 1, I lost the problem now. Hold on. It's not 1. I looked at the wrong thing. -5 and 4 plus 3i. Where f of 2 is 91. So find the polynomial given roots 5 and 4 plus 3i where f of 2 equals equals 91. All right, so now what? Right, so we look at this problem and we say I have to first make the factors and multiply them. Now, my favorite trick question of all time. How many roots do we have here? And if you say 2, I'm not going to be happy. How many roots do we have here? Now you're bothered that I didn't let you make a mistake and then correct it. Because the obvious answer would be, hold on, you just have 2 numbers there. There's the -5 and then... But I did say something about complex roots. I know I did. Does anyone remember what I said about complex roots? What did I say about complex roots? They always show up as what? The complex conjugate pair. So what is the complex conjugate pair on 4 plus 3i?
What's the complex conjugate pair?
Yeah, what is the complex conjugate pair? Oh, you're asking me what is it? We mentioned that when we did the complex review. We know what the conjugate means from square roots. So it means the same, right? Because this is square root situation. So complex conjugate pair would be the same numbers, opposite sign in the middle. So you technically have, anytime you see a complex value as a root, you instantly know that the opposite one is there, even if it's not written.
Oh, I see.
So what's the other one?
It says if z equals a plus bi, then z equals a minus bi, so
Yes.
before minus 3i.
Beautiful. There you go. So what are my factors? X plus 5, x minus 4 plus, minus 3i, and x minus 4 plus 3i. There we go.
How do we know there aren't more factors?
This is what the
Not
problem...
more roots.
This is what the problem said. Find the polynomial given these roots. So they gave you all the roots they wanted to give you. They gave you that. You don't have a polynomial to right? So what you know is that when you see 3 roots, you know that you're going to end up with the x cubed polynomial. That's what you know, because now you are doing the problem backwards. Earlier, you get the polynomial, you look at the leading coefficient, leading term, exponent, and you say, oh, x to the 4 roots. Now you are given 3 roots. Well, you were given 2, but you know there is a third one because complex always travel in pair. So you know you have 3 roots, and because you have 3 roots, your answer at the end will be x cubed. All right. So now let's just FOIL all of this mess and get our answers. Now, when you have complex roots, you multiply those first. So, and this is going to be 9 things because you have to go x into each, -4 into each, and so on. So x squared minus 4x plus 3ix. So you're done with x. Now you go for -4x plus 16, -12i, and now you go with the 3i. -3ix, +12i, and -9i squared. Fits. X plus 5. So now, look at the I terms. That's why they're complex conjugate. They cancel. You see them? And the only stuff that is left is real. You have your x squared minus 8x, right? -4, -4, plus 16. And this 9i squared, that I squared is -1. So that's plus 9 now at the end. So you have your x plus 5 to be x squared minus 8x plus 25. The only thing that it's left is to now FOIL this. Now look, all of the complex stuff is gone. So no more complex values. The only thing that now you need to do here is to FOIL this last part. So let's do that. X times it. Here's your x cubed. Aha. Minus 8x squared plus 25x plus 5x squared minus 40x and plus 125. So that is going to be x cubed minus 3x squared minus 15x and plus 125. All right. That's how we get the polynomial. There is one more thing that we did not discuss yet, and I have to fix it in a problem, and that is they give you this piece of information. So what do we do with this now? Well, one thing that I neglected to mention here is that these polynomials can be shifted up and down, right? Or stretched. So I'm just going to stretch this to fit. So I need to figure out this A. And that's why I have f of 2 is 91. It's going to help me do that. 91 is equal to A, 2 cubed, minus 3 times 2 squared, minus 15 times 2, plus 125. And I can compute this A. And I will explain why this is. Let me just go through this calculation and you will see where this A comes in the previous problems that we did. So this is 91 equals A. Then I have my 8 minus 12 minus 30 plus 125. 91 equals A. So minus 30, that's negative 95, right? And then take away 12, no, positive 95, what I'm talking about. And then take away 12, that's going to be 83. And then plus 8, oh, that's 91. So A actually is 1. So because A is 1, the polynomial we are looking for is the original polynomial that we got, which was x cubed minus 3x squared minus 15x plus 125. Now, okay, we did this, and now the question is why did we do this at all? Let me bring you back to the previous problem. I don't have to go far. If you FOIL this, what are you going to get on a first term? X times x times x times x. You're going to get x to the fourth when you multiply it back. Did we start with x to the fourth? No, we started with 3x to the fourth. Now, this guy of 3x to the fourth actually is encoded right there, but we don't see it. So technically, this last factor, right, could be written as 3x plus 1. So if I write the last factor as 3x, because 3x plus 1 will give me, right, if I say that equal to 0, it's going to give me x equals negative 1/3. And if I have x plus 1/3 equals 0, is also going to give me x negative 1/3. So which one is it? The one that we have or the one that we should have? Right? So that's what that A is for, because you have the point through which the polynomial has to go through, and then that would fix it, and it would tell you in this particular case that that A is equal to 3, and when you put a 3 over here and distribute it only into this one, you can't distribute into each one, right? Because then you would have 4 3s. You just have 1 3, and you can distribute into any one of these. Clearly, you choose to multiply it into the last one to kill a fraction. And when you multiply it into the last one to kill a fraction, you get 3x plus 1, and that immediately fixes all of the issues, because you will have 3x to the fourth as the first term, and you will also have the last term match what you have up there. Now, we'll have to do more of these examples next class, because we ran out of time now. We'll do more of this next class, and we'll go from there. All right, I'll see you next week. Bye.